Welcome. We're going to talk about, as you can see, graphing other trig functions. And by other trigonometric functions, we're referring to cosecants, secants, tangents, and cotangents. There's a previous video out there on graphing sines and cosine functions, so our focus is going to be on the other four. With that said, you may be a bit surprised by the first slide, where immediately we're going back and talking about sine and cosine graphs. But I want to talk about what I've referred to as the defining points, the points that give us our centerline points, our peaks and our valleys for sine and cosine. And I'm going to just, I think the best way to know this is to know these is to just have a feel for what the graph of sine looks like. For instance, the graph of sine, here's y equals sine of x. Goes from 0 to 2 pi at 0. It is 0. At pi on 2, it hits 1. At pi, it hits 0. At 3/2 pi, it's down at -1. At 2 pi, it's 0. That's what I'm referring to as the defining points. But I'm going to build that from a rotational perspective. Let's assume that this is a unit circle where this distance is 1, this distance is 1, etc. And we just start rotating, taking a tour around this, but we're just going to look at the quadrantal angles. So this point right here would be 1, 0, which would make x 1, y 0, and r is always 1 as we tour around a unit circle. When we reach this point, we are at 0, 1, giving us an x value of 0, y value of 1, and r, of course, is 1. By the time we continue our tour around to 180 degrees, or pi, we now would be at a point -1, 0, making x -1, y 0, r is always 1. At 270 degrees, or 3/2 pi, this point would now be 0, -1. X, of course, then is 0. Y is -1. R is always 1. Okay, so we come back up to sine. We're going to create our sine chart here, and we see that, and we know that sine is y on r. So as we tour around this, our first location right here, we get y on r 0 on 1, and 0 on 1 is 0. And we go to pi on 2 up to here, and we get y on r 1 divided by 1 is 1. We continue around to pi, and we get y on r 0 on 1, 0. At 3/2 pi down here, y on r -1 on 1, -1. And then back to 2 pi, right back to here, y on r back to 0. And note, those points, those ordered pairs, 0, 0, pi on 2, 1, pi 0, 3/2 pi, -1, and 2 pi 0 are our defining points on the graph. Now, I think much easier, at least for me, much easier to just remember this. It goes from, the sine goes from 0 to 2 pi and takes the shape it does, and I can come up with all of these ordered pairs for sine just by knowing that. Okay, let's take the tour with cosine. So give myself a little bit of room up here. Again, do we have to do this tour? No, but maybe if you're not good at memorizing graphs, maybe you'd like to. So let's look at y equals cosine of x. The graph of cosine of x looks like sine of x. However, it starts up at 1, goes down to -1, and takes on this shape. Ooh, that was bad. I can't let myself get away with that. Let's try that again. Okay, so cosine, let's do this one in green, x on r. So as we tour around at 0, x on r, 1 on 1. As we turn to 90 degrees, pi on 2, x on r, 0 on 1. We rotate around to pi, x on r, negative 1 on 1. And to 3/2 pi, x on r, 0 on 1. Back to 0 or 2 pi, x on r, 1 on 1. And we take a look at our graph and look at these ordered pairs. 0, 1. Pi on 2, 0. Pi negative 1. 3/2 pi, 0. There are our defining values. And those I'm going to use in a process I call rubber stamping. If you've seen the sine and cosine graph, graphing video, you know what I'm referring to with rubber stamping. If not, you're going to see it in play on the next, in the next couple of slides. Okay, now let's consider rotating around tangent, cotangent again. Same idea, but now we're rotating around for tangent and cotangent. But this point would still be 1, 0. X is 1, y is 0, r is 1. 0, 1. X is 0, y is 1, r is 1. Negative 1, 0. So if I forget my rubber stamps, I guess I could always do this, but if I know what the graph of the functions look like, I shouldn't have to. X is negative 1, y is 0, r is always 1, and 0, negative 1. X is 0, y is negative 1, r is 1. So one thing I want to talk about is the signs of the functions, and you might have heard this one before. Quadrant 1, all. Quadrant 2, students. Quadrant 3, take. Quadrant 4, calculus. All students take calculus, which basically means they're all positive here, all trig functions. Sine is positive here. If it is, then so is cosecant because they're reciprocals. Tangent is positive in third quadrant. So is cotangent, its reciprocal function. Cosine is positive in quadrant 4. Therefore, so is secant, its reciprocal. Now, if we consider our tour for sine, as we tour around the circle sine, we go through a positive quadrant, into a positive quadrant, into a negative quadrant, into a negative quadrant, further from there. So we have to go all the way around the circle till we repeat our positives. Therefore, cosine has a period of 2 pi. Consider sine, or sine has a period of 2 pi. Consider cosine. We tour through a positive quadrant. We tour through a negative, through another negative, and finally through a positive. So it goes positive, negative, negative, positive. Again, we have to go the whole way around the circle till we repeat our positive cycle, or till we repeat, if we start our positive cycle here, we're positive all the way around to here, and then we have a negative cycle starting back at this point. But not tangent. Tangent goes positive, negative, positive, negative. Therefore, the period of positive is just pi, and that's why you note over here I have counted by smaller increments pi on 4s. Well, let's start our tour of tangent. Tangent being y on x. And if I start at 0, right here, I get y on x, 0 on 1, 0. I move up to pi on 2, and I get y on x, 1 on 0. Undefined, but that was at pi on 2. What happens at pi on 4? At pi on 4 in here, we have 45-degree angle here, which makes x equal to y. And if x is equal to y, at pi on 4, y on x is 1. Likewise, 45 here, or 3/4 pi revolution to here, y is not equal to x. Y is actually the opposite of x. And if y is the opposite of x, y on x at 3/4 pi is negative 1. And at pi, we continue on, and we get y on x, 0 on negative 1, we're back to 0. Let's do a little backwards revolution for a moment. What if I went backwards? That wasn't a very good 45, but let's play along with me. Right here, y is not equal to x. Y is the opposite of x, making negative pi on 4 tangent negative 1. How about negative pi on 2? Y on x, negative 1 on 0, undefined. Now, I like using those values right there for my defining values because those lock me in between between pairs of asymptotes. So you'll see what our graph of that guy looks like. I've got room to throw it up top here, create a little bit of room. So if I was to graph this guy now, y is tangent of x using these defining points that I put over here. I'm going to go to negative pi on 2 over to pi on 2. At negative pi on 2, we have an asymptote. At pi on 2, we have an asymptote. At negative pi on 4, we're down 1. At 0, we're 0. And at pi on 4, I'm up 1. Well, that gives me a pretty good idea what our curve looks like. Okay, so I like working tangent from negative pi on 2 to pi on 2. Okay, I need to clean some of this up to talk about cotangent, but certainly not all of it. All right, so for cotangent, now we're dealing with the ratio x on y. I'm going to start at 0. When I start at 0 with cotangent, x on y, 1 on 0, asymptote, I like it. When I move around here, x on y at 45 degrees or pi on 4, x equals y, so 1. X on y here, 0 on 1, 0. At 3/4 pi, x doesn't equal y, x equals the opposite of y, so cotangent of 3/4 pi is negative 1. And as we move around to 180 degrees, x on y, negative 1 on 0, undefined. I like dealing with cotangent from 0 to pi. So our cotangent graph I might define as being, let's go one more tick mark here, asymptotal at 0 and pi. At pi on 4, we're up 1. At pi on 2, we're up 0. And at 3/4 pi, we're at negative 1. Okay, sort of looks like an upside down tangent graph, but with a little shift on it. So I like dealing with cotangent between 0 and pi, tangent negative pi on 2 to pi on 2. Okay, let's put this into practice. And we immediately start with the cotangent graph. And I would claim this, if we know what the cotangent graph looks like, we just looked at it. Typical cotangent looks like this. There's our defining values. We just talked about it. You can back up the video if you need to. Looks like this. How would this graph vary from typical cotangent? Well, I would say it would be pi times as fast. If I said it was 2 times as fast, and the period normally takes pi, try that again, pi, then if it's 2 times as fast, now everything would happen in pi on 2. We divide it by 2. 3 times as fast, pi on 3. Pi times as fast, our period is normal cotangent pi, but pi times as fast. The period is plain old ordinary 1. This is post function, which means we're multiplying the y values. What used to be up 1 is now up 3. What used to be up 10 is now up 30. What used to be down 2 is now down 6. 3 times as tall. So I would suggest we could do this conceptually. We ought to be able to just come up with this graph and say cotangent, normally 0 to pi, now 0 to 1. Quarter that. And now take our points. What used to be up 1 is now 3 times as tall as that. What used to be 0, 3 times as tall as 0, 0. What used to be down 1, though, 3 times as tall as negative 1, 3 times negative 1, negative 3. There's our graph. Now, with that said, let's go ahead and go through the rubber stamp process that I've talked about. What I would do first is I would choose a value of x. I would multiply that by pi. I would put that into cotangent, and then I would multiply by 3. That is our order of operations if we chose a value of x, how we would get out of this. So, the key here, into cotangent. Think a slide before. What values do we go into cotangent? 0, pi on 4, pi on 2, 3/4 pi, and 2 pi. What come out? Well, it's defined between the asymptotes. Pi on 4, first quadrant, oh, that must be a 1. First quadrant, then 0, then -1. In my stamp, my next step is to multiply by those values by 3. Undefined times 3, undefined. 1 times 3, 0 times 3, -1 times 3, and undefined times 3, undefined. Now let's go backwards to get back to x. I have to actually divide pi here. 0 divided by pi, pi on 4 divided by pi, pi on 2 divided by pi, 3/4 pi divided by pi, and 2 pi divided by pi. Oh, that's not 2 pi. I'm sorry. That should not be 2 pi. That matches a mistake that I made. Okay, this should be pi. Should just be pi divided by pi, should just be 1. And so let's check those points out. Here is 0 asymptote. 0 asymptote. Here is 1/4, 3, 1/4, 3. Here is 1/2, 0. Now there it is. 3/4, -3. Got it. 1 asymptote. So there we go. There's our graph conceptually and mechanically. All right, let's take a look at another graph, other type. Cosecant. Oh, we didn't talk about cosecant, but don't forget, cosecant is the reciprocal of sine. Here we have two pre-functions. I'm going to choose x, multiply by 2, and subtract pi before I ever get to cosecant. I would stamp this. So here is how we're going to treat cosecant graphs. I would choose x, I would multiply by 2, I would subtract pi. I then want to take the cosecant. And you can create a rubber stamp for cosecant, but I'm going to use sine, its reciprocal. I'm going to take the sine. And after that, I don't have any post function, so I would be done at that point. Here's why I call this rubber stamping. This section right here, let's do that in a different color. This section of the chart right here, for every sine graph I chose to use this mechanical process, I want 0 to go into sine, and then pi on 2, then pi, then 3/2 pi, and then 2 pi. Sine of 0, I'm thinking graph here. Right now I'm thinking about this. 2 pi, sine of 0, 0, sine of pi on 2, 1, back to 0, back to -1, back to 0. I don't have that data memorized. I do have the chart memorized. Now, work backwards. I need to add pi to get back to row 2. Add pi gives me 3/2 pi, gives me 2 pi, gives me 5/2 pi, gives me 6/2 pi, or 3 pi. Divide 2 or multiply 1/2 gives me pi on 2, 3/4 pi, pi, 5/4 pi, and 3/2 pi. I really want to strongly recommend you write these with common denominators. I think it helps. One, note that if you get a common cadence, in other words, I keep going up by pi on 4s, that I'm in good shape. 2, it's going to help us when we lay out the chart. So least common denominator, this would be 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi, 6/4 pi, which tells me 2/4, 3/4, 4/4, 5/4, 6/4, which tells me I did my backwards work correctly because I have a common cadence, and it tells me I should be making steps by 1/4 pi to get from one to the other. Huge common mistake. People will set this up and say, well, let's just start here at pi on 2, and then my next interesting value occurs at 3/4 pi, and my next one is at pi, etc. And then you notice what they've done here. This is 1/4 pi. This is 2/4 pi. We haven't spaced this out correctly. That's a big mistake in setting these graphs up. So that's why I like to think in terms of my common cadence is by 1/4 pi. So I'm going to count 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi. 5/4, 6/4, 7/4, 8/4. I may not need to go that far. And let's graph this as if it was a sine graph. So my first point, I have 2/4, 0, 2/4, 0. My next point, 3/4, 1, 3/4, 1. 4/4 gets me back to 0. 5/4 gets me down to -1. 6/4 gets me back to 0. And I'm in good shape here. That's a full period of the sine graph. Of course, this is not a sine graph. This is cosecant. I'm going to build it back to the y-axis. And this is the mistake a lot of people would have. They wouldn't have this tick mark right here. And they would put the next point from here at that spot. Of course, we don't want to do that. Oops, put my axis back in here. That was a mistake. We want to put the next point one tick mark over, one down, and actually back to the y-axis we're there. Okay, tempting to draw the curve in, but this is a cosecant graph, and cosecant graphs are the reciprocal. Reciprocal of 0, undefined. Our center line points are asymptotes, always, on secant and cosecant graph. Why did I lose my pen ability here? Let's try this again. There we go. Temporary malfunction on the smartboard. Okay, my other points. Somewhere on the sine graph along to getting here, I hit a height of 1/2. The reciprocal of 1/2 is 2. These act, it's improper to say they're parabolas, but they look like parabolas. Parabolas don't have asymptotes, however. So our graph looks like this. And we could go on building more of that just by taking our little sine points and continuing those on. Okay, so there you have it, a cosecant graph with a rubber stamp. All right, let's move on. Here is a tangent graph. Now, I would suggest we could do this conceptually. The period of tangent is pi, so if I take pi divided by pi, the period is 1. This graph looks just like tangent, except it's half as tall and upside down. But let's go ahead and stamp this and go through that process. Choose an x, multiply by pi, find the tangent of it, multiply by -1/2. And what values do I want to go into tangent? You might have to rewind to see this, but the values I like going into tangent are -pi/2, -pi/4, 0, pi/4, and pi/2. And I swear to you, I did not memorize that. Right now, I'm not looking at it, but I'm seeing it in my head. Graph of tangent goes from -pi/2 to pi/2 and looks like this. And there are all of my defining values. The asymptote, try that in a different color, the asymptote, this point, this point, this point, and the asymptote, which means I go from asymptote to -1 to 0 to 1 to asymptote. Let's continue down the chart. Multiply by -1/2. Undefined times -1/2. Undefined. 1 times -1/2, +1/2. 0, -1/2, and undefined. Build up, I have to divide pi. Well, that's easy enough. -1/2, -1/4, 0, 1/2, and 1/4. Oops, that's wrong. 1/4, excuse me, and 1/2. So I'm just going to count by 1/4. You might want to put -2/4 up above. -2/4 here, +2/4 there. But I'm going to count by 1/4. 1/4, 2/4. -1/4, -2/4. So here's my points. Let's go. -1/2 gives me an asymptote. Positive 1/2 gives me an asymptote. Negative 1/4. Try again. Having some issues here. Negative 1/4 gives me 1/2. Negative 1/4 gives me 1/2. Negative 1/4 would be right in here at a half. 0 gives me 0. 1/4 gives me negative 1/2. And that's enough guidance with my defining points to draw my tangent curve. Okay? All right. Let's look at a secant graph. I'm going to stamp this one, although I would suggest we could just draw a cosine graph, the reciprocal. The period now would be 2 pi divided by pi, or pi, and we'd move it down 3. But let's stamp this guy. I'm going to choose a value for x. I'm going to multiply by pi. I'm going to take the cosine. I'm going to subtract 3, and that's my chart. And the values I like to send into cosine start with 0, go to pi on 2, to pi, to 3/2 pi, to 2 pi. Cosine of 0, I don't have this memorized, but I have this memorized. I don't have the data memorized. 2 pi. Cosine starts up at 1, goes down to 0, to negative 1, to 0, back up to 1. Subtract 3. Minus 2, minus 3, minus 4, minus 2. Excuse me, minus 3. I got going too fast there. Minus 3, minus 2. In reverse, divide pi or multiply by 1 on pi, and I get 0, 1/2, 1, 3/2, 2. So there are all of our points. Now, I've said before on this rubber stamping, you can probably get by with just the first 2 columns if you have an idea what it looks like. So let's try that. I know I have values starting at 0 up to, and I'm starting at 0 and I'm moving to the right. So 0, 1/2, 1, 1.5, 2, and that might be enough for us. We'll see. But let's assume we only knew the first couple points. So my first point is at 0, negative 2. And my next point is at 1/2, negative 3. Now the question should be, where do I go from there? But cosine graph starts at a peak. So if I went down the first step, I should go down again. Another way to look at that is our center line is negative 3. Our center line is right here. I've got waves above and below. This point was above. I need to drop below down to negative 4, come back up, and now recover up to here. Okay? 0. Isn't that interesting? Boy, did I make a mistake on that one. Glad I caught that. I know some of you were waiting for me to find that. I don't know why I started at 1, negative 2. My first point is at 0, negative 2. Then I have a point at 1/2, negative 3. Now that just gets me to center line, so I have to continue down. 1 gets me to negative 2. 3/2 gets me back to center line, and then I have a peak. Okay, how do those points that I just put on compare to all of the rest of those ordered pairs? After my mistake, I think I've corrected it pretty well. And those are our points, but that is the cosine graph. And we're not graphing a cosine function. Therefore, we need asymptotes at the center line points. I'm going to be a little bit low on the graph here. And once again, all sorts of technical challenges with my pens today. Asymptotes at center lines. This point's getting sucked up into the asymptote. This one, running out of room here on my area here, but I think you get the point. And that would be a full period tied into the y-axis. I might be tempted to extend this. I know an asymptote's coming. I'd have another point here, so up. I know an asymptote's coming this way. Up into that asymptote. Okay, so apologies for kind of running out of room on the low end here, but I think you get the picture. Okay, we got possibly one more to look at. Nope, that's it for us for today. Hope that's helpful. You may want to review over that. I know I had a lot of students missing today. Hopefully you have watched this. Good luck to you, and let me know if I can help.